Stars. In this lesson, we're going to explore the science and engineering practices of developing and using models, using mathematics and computational thinking, and obtaining, evaluating, and communicating information. Our cross-cutting concepts include scale, proportion, and quantity, energy and matter, and stability and change. The formation of a star. A star is formed when dust and gas is drawn together by gravity. The cloud of dust and gas, called a nebula, becomes hotter and denser, collapsing in on itself to form a protostar. When the center of a protostar is hot and dense enough, nuclear fusion reactions begin, and the star begins to shine. The hydrogen nuclei in the star's core fuse together to form helium nuclei. Fusion releases a huge amount of energy. This keeps the center of a star hot enough for fusion to continue and heats the gases in the star. The hot gases in the star expand, creating an outward force that balances the inward force of gravity and stops the star collapsing. The star remains stable as long as these forces are in equilibrium. It is in the main sequence period of its life cycle. So how do stars begin and end? The birth and death of a star. A star is a huge glowing ball of hot gas, mostly hydrogen and helium. A star is born in a huge cold cloud of gas and dust called a nebula. The nebula slowly contracts under its own gravity, and a clump of matter forms inside the cloud. Gravity continues pulling in more matter, and the clump collapses inward. The clump becomes more dense, gets compressed, and begins to heat up. Eventually, the core of the collapsing clump becomes so compressed and so hot that nuclear reactions start. Hydrogen fuses to form helium, which releases energy and causes the star to shine. When the hydrogen is used up, the helium core collapses and the outer layer expands and cools. The star shines less brightly and is now called a red giant. The death of a star after the red giant stage depends on the size of the star. After a small star like our sun has become a red giant, its outer layer drifts away into space. The hot, dense core that remains is called a white dwarf. The white dwarf cools and eventually stops shining. After a massive star has become a red giant, nuclear reactions in the helium core continue and form other elements around an iron core. The collapse of this core causes a huge explosion called a supernova. The remains of the core form a tiny, very dense neutron star. Really massive stars are similar to massive stars. From the red giant stage, nuclear reactions create an iron core, which explodes as a supernova and forms a neutron star. The difference for really massive stars is that the core of the neutron star collapses further, and this results in a black hole. Structure of a stable star. A star is not a uniform ball of burning hydrogen. Its inner environment varies significantly as you move from the surface to its core. The radiative zone. Nuclear fusion in the core releases photons, which travel through the other layers of the star. Some of these photons transfer energy to matter in the star, and some travel directly to the star's surface. The core. Due to extreme pressure, the core of a star is where the temperature is greatest, roughly 14 million degrees Kelvin. This is where most fusion occurs, releasing huge amounts of energy. The convective zone. Some energy from the core is transported through the star by convection. Matter close to the core heats and rises up through the star. The energy is transferred to other parts of the star, and the cooled gases sink down again. The corona. The corona is a low-density gas layer which surrounds the star. It is very hot despite its low pressure. The corona can be observed during a total eclipse of the sun, when it forms a glowing ring around the moon. So let's talk about some of the terms that we've already discussed. A nebula is a cloud of gas and dust from which a star is born. A red giant is a star formed when hydrogen in the star is used up. A supernova is an explosion when a large red giant collapses. A white dwarf is formed at the end of the life of a small star. A neutron star is a very dense star formed after a supernova. And finally, a black hole, formed by the collapse of a neutron star. The death of a small star. The end of a star's life cycle depends on the size of the star. What happens when a star, the size of our sun, runs out of hydrogen in its core? Stage 1. When the hydrogen in the star runs out, the star will expand. The photosphere cools and dims, and the star becomes a red giant. Stage 2. In the core of a red giant, the high pressure and temperature cause helium nuclei to fuse together. Heavier elements such as carbon, nitrogen, and oxygen are formed. Stage 3. The outer layers of the star are cooled and still contain hydrogen. Hydrogen fusion still occurs here. This is what causes the outer layers to expand while the core contracts. Stage 4. When all the helium is exhausted, a low-mass star like the Sun lacks the mass to compress the core further. The outer layers of the star drift away. The dense core becomes a white dwarf star. And in stage 5, there is no fusion in the white dwarf, causing it to cool. Scientists think that eventually a black dwarf star will form. Luckily, the Sun will be stable for another 4.5 billion years. So what is a white dwarf? A white dwarf is formed at the end of the life cycle of a star that is about the size of our Sun. This photograph was taken using the Hubble Space Telescope. It shows ancient white dwarf stars in the Milky Way galaxy. The white dwarf stars are shown ringed in blue. So let's revisit the life cycle of small stars. What is the order of stages in the life cycle of a small star? Number 1, a nebula contracts under its own gravity. Number 2, central mass of the matter in a nebula heats up. Number 3, nuclear reactions start in central mass. Number 4, the star shines. Number 5, hydrogen runs out and a red giant forms. Number 6, the outer layer of the red giant drifts off into space. And number 7, the white dwarf is formed. The death of a large star. Let's explore the death of a massive star. The Sun is a relatively small star. How would its fate differ, as we've already observed, to a much larger star? Stage 1, massive stars expand when nearly all the hydrogen has been used up. They expand to a much greater size, becoming red supergiants, fusing hydrogen in their outer layers. Stage 2, the core's huge mass generates extreme temperatures and pressures. This means increasingly heavy atoms are able to form by fusion. The biggest stars are able to produce iron cores. Stage 3, when the core is mostly iron, the star explodes in a supernova. The large amounts of energy produced in the explosion means elements heavier than iron can be formed. And in stage 4, after a supernova, all that is left is the star's collapsed core, composed mainly of neutrons. This is a neutron star. Finally, in stage 5, the biggest stars become so dense as they contract that even light is unable to escape their gravitational pull. In such cases, a black hole is formed. So let's explore the order of stages in the life cycle of a massive star. Number 1, nebula contracts under its own gravity. Number 2, central mass of matter in a nebula heats up. Number 3, nuclear reactions start in central mass. Number 4, the star shines. Number 5, hydrogen runs out and a red giant forms. Number 6, collapse of the core of a red giant in a supernova. And number 7, dense neutron star is formed, which may collapse. So what is a supernova? A supernova explosion is one of the most energetic events in the universe. A supernova occurs at the end of a massive star's stable life, when all of its hydrogen atoms have been fused into helium atoms, and its core is being compressed by gravity. The heat generated by the compression core makes the star increase to 100 times its original size. The high temperature causes the helium atoms in the core to fuse, forming heavier elements such as carbon and oxygen. Once all the helium has been used up, gravity forces the core to shrink again. This causes the newly formed heavier elements to fuse into elements such as neon and magnesium. The core becomes denser still, and the oxygen atoms fuse to form silicon and sulfur. The silicon and sulfur fuse together to form iron in the tightly compacted core. When the core reaches maximum scrunch, it collapses at a speed of 45,000 miles per second. A shock wave spreads through the star, and matter is hurled through its outer layers and into space. This explosion, as the star collapses, is the supernova. After a supernova, all that remains is the star's collapsed core, which is called a neutron star. Neutron stars rotate rapidly, and some pulse radio waves into space. These are called pulsars. Neutron stars. After a 1.4 to 2 solar mass star has exploded in a supernova, only the inner core of the star remains. This core will have a radius of only 10 kilometers and a density more than 14 orders of magnitude higher than that of the Sun, and close to the density of an atomic nucleus. This is a neutron star. The outer shell is thought to be composed of a solid crust of atomic nuclei. Inside this crust is a liquid interior composed almost entirely of neutrons, increasing in density towards the center to reach nearly 10 to the 18th kilogram. Some neutron stars rotate, emitting two beams of radiation in opposite directions. If the path of these beams crosses the Earth, the star can be observed as a regular pulse of radiation. When the first of these regular pulses was observed in 1967, its origin was known and was dubbed LGM1. Little Green Man. Shortly afterwards, it was established that the pulses came from a type of star, and the phenomena was called a pulsar. Pulsars rotate at speeds ranging from one rotation every few seconds to hundreds of rotations a second, and each rotation causes two pulses of radiation as the two beams pass over the Earth. How are black holes formed? The end of the life cycle of really massive stars is different to that of massive stars. After a really massive red giant collapses in a supernova explosion, it leaves an object so dense that nothing, not even light, can escape its gravitational pull. This is called a black hole. Some scientists believe that there are black holes at the center of galaxies. If light cannot escape from a black hole, then how can a black hole be observed? Event horizons. Every black hole is surrounded by an event horizon. Nothing that occurs within its boundary can ever affect the universe outside it, and anything that crosses this horizon will fall into the black hole. To an outside observer, an object falling into the black hole slows down as it approaches the event horizon, never quite crossing it. From the object's point of view, it crosses the event horizon and falls towards the singularity. The study of these strange effects, in which time and space are different depending on the observer, is known as relativity. The event horizon is not a physical boundary and cannot be seen. It is only a theoretical boundary that separates the black hole from the rest of space. So let's look at an animation to help us understand. A black hole cannot be seen directly. No light escapes from a black hole, so it cannot be viewed directly. Instead, the effect of its huge gravitational pull on nearby matter can be observed. Matter from a nearby star can spiral into the black hole. As this happens, the star matter emits X-ray radiation, which can be detected from afar. This is a real X-ray image of a galaxy. A bright stream of X-ray radiation is being emitted from the central X-ray source. Scientists believe this source is a black hole. Elements on Earth. Where do Earth's elements come from? The early universe contained only the elements hydrogen and helium, which were formed soon after the Big Bang. How are elements heavier than this found on Earth? Our solar system is believed to have been part of a star-forming region, where early stars formed and exploded as supernova. The atoms present in the solar system would have been from one or more of these events. The heavy elements that formed in the dying star were scattered by supernova. Over billions of years, gravity pulled the atoms from the supernova together to form large objects such as the sun. Gravity also pulled atoms together to form the planets around our sun, including Earth. The elements present on Earth have remained largely unchanged since the Earth was first formed. The atoms are just combined in different ways. This means that we and the things around us are all made of stardust. All right, filling in the missing words about forming large atoms. Let's go through each one of these. Inside the sun, the main fusion reaction taking place is hydrogen fusing to produce helium. In a red giant, the high temperatures and pressures in the core lead to the fusion of helium to make heavier elements. Initially, elements such as carbon and oxygen will form. Large stars may even be able to produce iron. The explosive power of a supernova is required to produce the heaviest atoms, such as silver, gold, and even uranium. And the heavy elements found in our solar system must have been produced by an old star. This may have been quite distant, with a powerful supernova forcing heavy atoms through space and into our solar system. All right, let's match the star life stages to the elements produced. Main sequence stars predominantly are only producing helium. Red giant stars are going to produce carbon, nitrogen, and oxygen. Red supergiant stars will produce magnesium, neon, silicon, sulfur, and iron. And supernovas will produce silver, gold, and uranium. So how are elements formed? Consider designing a poster to communicate information about how different elements are formed in the universe. It could include answers to the following questions. How were hydrogen and helium formed in the early universe? How are elements heavier than helium but lighter than iron produced? How are elements heavier than iron produced? And how can scientists tell which elements are present in stars? Power output of a star. The amount of energy a star radiates per second in all directions is its luminosity. It's its power output. Stefan's law helps us to understand this, and it states that luminosity of a star is directly proportional to its surface area and to the fourth power of its temperature. So a cool red giant can have the same power output as a smaller but hotter star. Flux and the inverse square law. The more distant a star, the dimmer it appears. Why is this? The vacuum of space does not absorb light, so the total amount of light is not reduced as you get farther away from the star. But the farther away you are, the larger the sphere the light is spread over, so the lower the intensity of the light. This intensity is called flux. It measures the power per square meter by dividing the total power, the luminosity, by the area of the sphere at that distance. Flux is inversely proportional to the square of the distance from a source. This is an inverse square law. Apparent magnitude. The apparent brightness of a star when viewed from Earth depends on the luminosity of the star and how far away it is. Flux depends on both of these, but varies over a huge scale. The apparent magnitude uses a logarithmic scale to give an idea of the order of magnitude of the star's brightness. The constant is based on the brightness of a comparison star, usually Vega, one of the brightest stars in the night sky. Apparent magnitude makes it possible to pull all celestial objects on a scale from roughly -30, the sun, to a +30, the faintest object visible in the Hubble Space Telescope. Absolute magnitude. Related to apparent magnitude is absolute magnitude. This removes the effect of distance by giving the apparent magnitude of a star if it were at a standard distance of 10 pc. If d is the distance to the star, then m is given by. If apparent magnitude is a logarithmic scale describing flux, then absolute magnitude is a logarithmic scale describing what other variable? It's luminosity. Some objects, such as certain types of supernova, always have the same absolute magnitude. If m and m are known for a particular supernova, what can you calculate using the formula above? You can calculate how far away that object is. So let's look at calculating brightness. If the apparent magnitude m of the sun is -27, what is its absolute magnitude? Using our equation, the absolute magnitude is 4.6. What is the luminosity of a star of temperature 4,500 degrees Kelvin with a surface area of 6.09 times 10 to the 18th meters squared? Correct answer, using Stephan's law, 1.42 times 10 to the 26th. What is the flux of a star of luminosity 1.42 times 10 to the 26 watts from a distance of 1 astronomical unit? The correct answer is 502. The Hertzsprung-Russell diagram. Comparing the temperature and luminosity of the stars. The temperature and luminosity of a star vary throughout its lifetime. These two variables can be plotted on a Hertzsprung-Russell diagram. This diagram shows temperature on the horizontal axis with lower temperatures on the right. Luminosity is measured relative to the luminosity of the sun, L0. Both are logarithmic scales. A star of one solar mass starts its life as a nebula, a cloud of gas and dust, collapsing under its own gravity. This star is shown on the graph using these values. T equals 2000 Kelvin. As the nebula collapses, it releases energy, increasing its temperature and luminosity to become a protostar. Fusion has not begun. Our temperature now is 3,800 Kelvin. When fusion begins, the star's temperature increases again, but its luminosity falls slightly. Our temperature is now 5,800 degrees Kelvin. Our luminosity is back equal to 1. The star is now on the main sequence curve. This is where all stars spend the majority of their life. The sun has been a main sequence star for 5 billion years and will remain that way for approximately another 5 billion years. After roughly 10 billion years on the main sequence, the star starts to die. It expands into a red giant, cooling but increasing in luminosity. So our temperature has decreased to 4,500 degrees Kelvin, and our luminosity is now around 100. Stars with a similar mass to the Sun form red giants when they die. But high mass stars towards the left of the main sequence form supergiants. Betelgeuse and Rigel are examples of these. When nuclear fusion stops, the red giant sheds its outer layers to become a white dwarf with a high temperature due to its high density but low luminosity. Our temperature is now around 10,000 degrees Kelvin, and the luminosity is 10 to the negative third. Other white dwarfs all lie on a curve well below the main sequence.